Hey YouTubers, it's Crafty Coder. Wanted to talk about the finale of the constant current dummy load project we put together. We've talked about it from breadboard to PCB and now finally constructed PCB and final project. I've got 8 of these built, 6 of them are out in the test lab in Maryland where they're being put to use testing some power supplies of mine. But this guy is for my lab. I've got it outfitted in a pipette tip case. It's got a DC voltmeter which measures the voltage across the load resistor. It's got the knob for controlling the output current, heatsink of course, input power, 12 volt CPU fan, and legs. CPU fan is to do active cooling on the MOSFET's heatsink, and at 15 amps, which is what I designed this for, it gets hot. Even when you're putting when dropping all the voltage to the resistor, the MOSFET's still hot. So you just can't get away from that. And well, let's talk about how it works. We'll show it in action, and we'll show you a close-up of the constructed one not in a case. So here's the board up close. We've got the MOSFET, we got the voltage input, the load output, we got a 5 volt regulator. We have 4 op amps here. We've got the switch for switching modes on the MOSFET gate, either flat voltage to the gate, which uses the gate as a variable load resistor essentially, or PWM, which means we fully saturate the gate and we turn it on and off. Still getting a precision amount of current going through it, although at any given level it's not the same voltage in these two modes, so I usually reset it and then put a PWM and then turn it up. We've got a 12-bit DAC, we've got an @tiny85 and a rotary encoder. The rotary encoder's sole purpose is to tell the @mega to adjust the output of the DAC. Here is a voltage reference, a 2.048 voltage reference, and this is a 12-bit DAC, so it just moves up 1/1000th of a volt each unit on the DAC. And here is a voltage divider which will cut that voltage down to almost nothing, the 25-turn trim pot. And so if you wanted to have a very low setting, you could use that to get the setting very low. This is another 25-turn trim pot, another 3000 ohm trim pot. Its purpose is to put gain into the first stage op amp. So if this is putting out, say 1 volt, the gain is set so that it starts at no gain and will go up to infinity gain, which takes you to, well, it's not quite no gain. It's a very little bit of gain. And it takes you up to the top end rail of the LM324. And when I run it at 12 volts, that's somewhere around 9 or 10 volts. And you can imagine 9 or 10 volts through a 1 ohm resistor. That's going to give you 9 or 10 amps. I use 0.1 resistors, which would be 90 or 100 amps, so I clearly don't use that. The gain when I'm running it with a very small resistor. And what these two guys are high-pass filter to get the jitter out of the op-amp reference, or the op-amp's first stage from the voltage reference input, so it's a nice flat voltage that goes through it. And what this switch does is when you put it in PWM mode, which I'll show you in the video later, it takes the very minor oscillations that come out of the second stage and boosts them up to infinity so that you get this fully saturation followed by a full cut of voltage. So you fully open and fully close the MOSFET quickly. And that's pretty much the layout. I'll show you the bottom. The bottom of the board, you see that I have all through-hole componentry. One little bodge here where I put on 2 capacitors on the rotary encoder to level it out some, and then I put some copper down on the high current leads so that I have lower resistance and less heat. And that's it. There's a handy set of headers here for measuring the load resistor, the voltage across it, and there's 5-volt I/O and ground there for putting that in or out, because that sometimes is necessary. And there you go. So let's show it in action here. We've got it set up on the bench. This pin is connected to the oscilloscope, and it goes to the gate of the MOSFET, just so you can get a sense of what it does in bias mode versus PWM mode. This guy is the load resistor. It is a 1 ohm load resistor. I've got it set up in a somewhat unusual fashion in that I allow you to connect any external load resistor to it. That's because I wanted to be able to test it in a bunch of configurations. Here's a 200 watt 0.1 ohm resistor, and that's important for when I want to do 15 amps, but not important for when I want to do a low current test like we're going to do here, because we're going to run it not out of my power supply but out of the BK Precision. So let's turn it up. And we are in what I call bias mode. So when we look at the scope, you'll see a nice flat line as we pass this simple voltage through to the gate, and we are pulling 1.2 amps out of the power supply, and 1.08 amps are being dropped through the resistor, and it will slowly warm up. These two leads here are connected to the multimeter here on the bench, so that's where I get that figure. Since it's a 1 ohm resistor, Ohm's law, 1 volt times 1 ohm equals 1 amp, so 1.08 amps. And this figure here is just a obvious clear backup, because it's clear how that works. Now, we can reset the system down to 0 by pushing the button on the rotary encoder. This drops down to 0, that drops down to 0, this drops down to 0, and now we'll put it in PWM mode. Just flick the switch, and we turn it up, and now we are applying a nice, well, it's almost a triangular wave with a little ripple on the bottom. And what that's doing is essentially doing a full saturation. As you can see here, the peak to peak is 10.4 volts. And since I'm putting 12 volts into the op amp, and the LM324 will give me out of 12 volts about 10 volts. And so I'm going all the way to the top rail where I don't hang out very long before I start to come down. And then there's an abrupt drop off. And you can see how the cap gets lower until it turns off. Now let's discuss the gain circuitry. We'll stick a screwdriver on the pot here. This is the gain pot. And we can turn it up. You can see the multimeter starting to ratchet up. Oopsie. Hard to get the screwdriver on while you run it. As you get closer to the bottom and the gain starts to ratchet up fast, it'll get out of control. I might even hit the current limiter on the power supply if I go too fast. You can see on the scope how the waveform is shifting. Yeah, now it's starting to happen fast. Ooh. Ooh, too far. There we go. That's about as far as I want to take it with this power supply. It's only a 5 amp power supply. But we can zero it out still really easily. And now when we control it, oops, wrong direction. Now when you control it, it just goes up. It goes from 0 up to that 4 3/4 amp area. Easy cheesy. And that pretty much shows off all of the aspects of the project except for actually attaching this guy, but you have a good sense of what that'll do. Just multiply the amps times 10 and everything else stays the same, essentially. One other thing of note is the answer to the question some of you may be asking yourselves: why did he make it so complicated? What's with the microcontroller and the DAC and the rotary encoder? Why not use a 25-turn trim pot? The answer to that is ease of use. I wanted to be able to zero it out fast with the push of a button, which is easy to do with a microcontroller and hard to do with a 10-turn pot. 10-turn pots are reasonably expensive. The encoder is probably the most expensive thing on the BOM, actually. I think it's about $3. The at Tiny is about a quarter, 35 cents or something. And the DAC, I forget what I paid for those, but maybe $2. I doubt that much. So you put everything together with the voltage reference, and you're still coming to a price of a 10-turn pot. And what you can do with software, what you can't do with a 10-turn pot, is you can set it up so that this will give me 10 turns to the full setting if I want to. But through software, I can have it sense the speed at which I'm turning it and go all the way to full in one turn if I want to, just by turning it fast. Same with going down. And that I released on the internet for you guys, so you can see that in a previous post on my channel.
Alright, so let's take a look at the schematic here and talk about some of the aspects. Let's start at the beginning. The beginning, I think, is the voltage reference. So the voltage reference starts here, and we take 5 volts that comes in from the 7805 and go through limiting resistor to 330, and then the voltage reference shorts to ground and lets through the 2.048 volts, and it's very close. It's within a thousandth of a volt, and that goes in to the DAC. Now the DAC is controlled by the @tiny85. The @tiny85 uses software to control the DAC through the rotary encoder, and it's got those 2 capacitors that I showed you bodged onto the bottom of the board there. I had only used one, thinking that one would do, but it did not. It had no effect at all, so it was a bad choice on mine, but I was able to fix it with after the fact, and I've updated the board, as you can see, with 2 capacitors, and now it's in good shape. Here is an ISP header that I used to program the @tiny on the board. So first thing I do is put the @tiny on the board, then I program it, and then I put in the rest of the parts. So we take the voltage output, we run it through the first of the 25-turn trimmer pots, which is a voltage divider, and that gives us our initial voltage into the first operational amplifier, which has the high-pass filter, which removes the jitter, as well as its own 25-turn trimmer pot, which is used shorted to ground to essentially put infinity gain, up to infinity gain, into the circuit, which allows you to get either at a minimum of whatever the DAC is outputting and a maximum of the high end, the top rail of the op amp. And since I generally power the op amp with 12 volts, because that's what my power supply uses, I get about 10 volts out of it. Well, the last test we saw just previously in the video is 10.4 volts. From there, I go into a second op amp, which then either drives the MOSFET directly or drives a third op amp channel. Now, If it drives the op amp directly, it gets a nice steady voltage out of it, which goes to the op amp, and then the op amp, or the MOSFET, and the MOSFET has a feedback loop that goes right back in. Now that feedback loop goes into both of these op amps, and this switch here, which is the bias PWM mode switch, just pumps it into, takes that signal and puts it through one more setting, which gives it infinity gain again, and bam, you have a full saturation mode or a more linear ohmic region mode, depending on how you want to use it. And that's pretty much it. All of this is just the power coming in and the current going out. So that's the load resistor outputs. And here is the power in, and here is the 7805. And that be it. Now let's go take a look at the board layout. First off, I'd like to make note here that the board is long and narrow. Now, the dimensions, as you can see, are 100 by 50 millimeters, and that selection was made not because it was somehow superior, but because that was cheap. And I don't think that's a very good reason to design a board layout. I saved, I don't know, $20 for 10 boards, so maybe something like that. So $2 at PCB. And what I got was this distance from here to here was too narrow for me to get appropriate spacing for my banana clips. Or not the best choice I've ever made in my life. I think I would have been much better off making it wider and paying the extra money. I'll let you guys change it if you see fit, but it's not ideal. But it works. Another thing worth noting here are the ISP headers. These are on here. I don't populate them, but you can use them to update the firmware on the @tiny85 with other code if you want. And I'd like to make note here that the capacitors that are on the bottom of the board you saw in person are now on top of the board with through-hole components, so it makes it easier to build properly. What those do is they debounce the mechanical rotary encoder circuit so that you don't get any dishonest reports of changes. This is particularly important with the firmware that I wrote that looks for consecutive turns in one direction and counts them and the time they came in to tell it how big of a step it should be. So the more consecutive and narrow amount of time, the bigger each step is, which gives you a sense of acceleration. But that only works if you don't have any drift or any fake turns of the pot. So I particularly needed that signal to be clean, and it is with the capacitors, but it wasn't with one. So the boards that I made are a little different than these boards, but in all the meaningful ways, they are exactly the same.
Well, guys, thanks for following along. We talked about the inspiration for this project, the hardware, the design some. We went over the schematic and the board layout. We talked about the software and why we made some of the design considerations we did, like having an MCU and a DAC and rotary encoder versus a 10-turn pot. We talked about why we put in the trim pots and why trim pots can be pretty handy in places where you don't exactly know how the circuit's going to respond, but you know where you might need to make changes, and so trim pots go in handy like that. I'm going to post the Eagle files, the schematics, and the board layout for you guys to take advantage of as just open source hardware. I'll post those up and link to it on the Freeside Atlanta Makerspace blog, where I'll post this video along with other resources for it. And I'd like to say I had a lot of fun working on this project. I came by it honestly in that I had finished building power supply and thought, man, I need a way to test this thing. What can I do? And after doing a little research, found that the best thing to do would be to make a precision load, and this was my first analog electronics project. I've done digital electronics now for about a year as a hobby, and analog electronics are a lot of fun. They're really different from digital electronics, and I urge all you guys who have any interest in electronics to give analog a try. Letting Newton into the driver's seat is a lot of fun, and I learned a ton, and I know you guys will too. So I hope you enjoyed the series. This is my first real attempt at doing sort of video blogging and stuff, and I'm inspired by what Mike's Electronics video blog, and Dave Jones' EV blog, and Martin from South Africa's blog, and there are a couple others out there that I enjoy a lot, and I thought I might be able to add a little bit of color to that story. So hope you guys enjoy it. Take care.